So today I want to look at the ballistic pendulum problem. So we saw the ballistic pendulum, the actual device in class. Here we're going to look at the theoretical construct, where we have some sort of object, let's say this ball, and it's pushed back against a spring compressed a distance x. And in the ballistic pendulum part, the ball is shot by the spring, it's caught by the cup, which swings on the boom arm up. The boom arm has a length L and it swings to an angle theta. So eventually we're going to have to figure out where this ball is going to land if we took the boom out of the way and we just shot it straight out here. There's some things we're going to need to know, like what is the mass of the ball. So the ball we're going to call it MB for M ball. We know it's getting shot into this cup. We're going to ignore the boom arm. We're going to say its mass is small. We're going to need the mass of the cup. We're going to use MC for the mass of the cup. X here is our compression distance. This capital H is the height of our table above the ground. L is the length of the boom arm. And we know it swings to an angle theta once it's caught. So what I like about this problem is that in the end, it's going to be a projectile problem. But before we get to the projectile problem, we know that there's an energy problem where we're going to see how high it swings. And there's also a conservation of momentum problem here where there's an inelastic collision between the ball and the cup. So we really have to work backward. We know it's projectile motion, so we're going to need to know how fast it's moving, the ball. But to get how fast it's moving, we would actually need to know something about the collision. And to know something about the collision, we're going to have to know something about the swing first. So let's take the energy part first. So let's take the energy of the swing. This is after the collision. So we know that when it swings here from, let's say, point A to point B, when it swings from point A to point B, we know there's a conservation of energy within the swing. So down here at A, it's all kinetic energy. Up here at B, it's all gravitational energy. So those are the theoretical constructs here. Some things we need to know, however, are, well, what M are we talking about? Now, I know that there's on both sides, you could divide both sides by M and they would magically disappear. But what M are we talking about here? This is after the collision, so this is the mass of the ball plus the mass of the cup. So again, they're going to magically disappear. But here's what we're left with. I want to find the speed. The half is something we know the gravitational field strength. What about the H? Looking at this picture, I don't see any H's, so we're really going to have to think about, well, what H are we talking about? And it's the swing height. So this is the height of the ball right after the collision. This is the height of the middle of the ball at the top of its swing. So that's the H we're talking about. So when I look at this problem, how am I going to figure out the H? Well, if I extend my dotted line back to the boom arm, what I'm noticing is that the boom arm has length L. The boom arm also has length L here. So this distance here, this H is also this H here, which makes this section L minus h. So if I look at this angle theta, that's the hypotenuse, this is the adjacent side. I can actually take a break from this for a second and we'll come back. Let's look at what the h looks like. So one thing we know about cosine, it's the ratio of the adjacent side to the hypotenuse. If I look here, my adjacent side is L minus h. The hypotenuse is L. I'm going to multiply both sides by L. I'm going to add h to both sides because that's what I'm looking for, and I'm going to subtract this from the both sides. And then simplify. So in this problem, the way it's structured, I'm looking up here and I'm given L and theta. How am I going to figure out my h? By figuring this using this cosine equation, I can get an expression for h. So now, if I come over here, I see this and this match, so I divide both sides by that term, and I'm left with if I substitute my h in here and simplify, I end up with v squared is equal to 2g and so this is going to let me figure out the speed, but what speed is that? This is the speed of the ball and the cup together right after the collision. And that is going to end up being an important construct here. That the speed that we solve for in this energy of the swing is the speed of the ball and the cup together after the collision. What about before the collision? Okay? Once we know this as an idea, we have to take into consideration what happened after the ball left the gun before it hit here. It was traveling fast, it hit this cup and it slowed down. But because it's an inelastic collision, that tells us that we lost a bunch of energy, but because it's a collision, we know momentum is conserved. So, we can use the momentum we can talk about the momentum of the collision, and we know that the momentum is conserved. So the initial momentum has to equal the final momentum. What was happening before the collision? What was the initial state? Well, it was the ball was moving by itself. So initial momentum was mass of the ball times the speed of the ball, the velocity of the ball, before the collision. After the collision, the ball has hit the cup and coupled and they swing together. So the mass is the mass of the ball plus the mass of the cup, and then what's their combined velocity? Well, it's what we solve for down here. So using this, we're going to use this figuring out h to get the h. We use that in here with this energy construct. We can find the velocity of the ball in the cup. If we know the velocity of the ball in the cup and each of their masses, I know the mass of the ball, I can find the velocity of the ball. So this is an easy way for us to find the velocity of the ball straight out. So what about the projectile part? Well, if we took this boom arm away, the ball got to the edge of the table here, we know it would shoot off and land basically right around here. And so the thing we're looking for is if I wanted it to hit a target, how far away would I have to put the target? No problem. But this becomes a projectile motion problem. And a projectile motion problem is something that we know how to do already. Whenever you're faced with a projectile motion problem, I would suggest break it up into its horizontal and vertical pieces and address them separately. So when I think about the vertical pieces, there are 5 variables in the vertical direction. And we know a couple of these. Okay? In this case, the change in the vertical is h. Actually, it's negative h because it's falling down. The initial velocity, now, we know that this is coming out fast. This ball is coming off here fast, and if the boom arm is not in the way, it's going to shoot off. But because this is the vertical direction, the initial velocity in the vertical direction is 0. That's crucial here. We don't know this, and they don't ask for it. The acceleration is -10. And the time is the thing we actually need to solve for. So, here's our parent equation. And so if we solve for t here, so this will give us the time that the ball's in the air. Then the question is, what if we want to know, we actually want to know how far it went, so then we have to consider the horizontal direction. These are our 3 variables for the horizontal direction. This is what we're solving for. The t comes from down here. And this is how the problem all links together. Is if I want to find the v in the x direction, well, it turns out the v in the x direction is the velocity of the ball coming off the spring, which we know right here. And that's how the problem links together. And if we know the velocity of the ball, and we know the time, we can figure out how far it goes horizontally. One other interesting thing that we can pull out from this is, I wonder if we could find the spring constant of the spring. We'll have to consider another part of this. We know the ball gets shot off with a speed equal to this VB here. And if we consider where the energy was before the ball was shot, it was all in the spring here. So let's consider the energy construct here. It was all in the spring, then it was all in the motion of the ball. So for the shot, we know that all the spring energy goes to all the kinetic energy of the ball. So these are our equations that go with these. Don't forget this little k is a spring constant. That's actually what we're solving for. X is the compression distance. We see here. V is the speed, and this time it's the speed of the ball, and M is actually going to be the mass of the ball. So if we rearrange this, the halves can go away. So if I want to find the spring constant, I need the mass of the ball, the speed of the ball as it comes off the spring, and we need the compression distance. And that'll give it to you.